Okay, so this moment of inertia that you're looking at, the rotational mass. Okay, what if you have multiple masses? What you need to do is, if you got multiple masses, you have to sum up the masses and the squares of the radial distance. Distances with respect to the point of rotation. All right, so what is that supposed to mean? So what that means is something that we will see shortly. Okay, so we got the rotational dynamics. So from torque, we end up getting the rotational inertia. So the force is what causes the acceleration. All right, so acceleration becomes the angular acceleration. The mass becomes the rotational mass. Mr squared is our rotational mass. All right, if you have multiple forces, obviously you can sum up the forces. If you have multiple torques, you can sum up the torques by summing up the individual moments of inertia, in essence. All right, so this is an interesting concept. What if you have multiple masses? What happens? Okay, so one of the things you need to know is the moment of inertia is going to depend on where the rotational axis is. Okay, so imagine that you have two masses, and you can take one mass and rotate it with respect to the other mass. So a rotational axis is going to be located right here. Right, so you're just spinning it in this direction. So omega represents the angular velocity of it. So the distance between these two masses is going to be r2. So r2 is the distance to the second mass. Okay, so if you're looking at the moment of inertia, and you have to kind of sum up the moment of inertia each and every single mass, m1 times r1 squared. R1 is going to be the distance to the point of rotation. In this case, r1 is going to be 0. And 2 times r2 squared. R2 is going to represent the distance to the point of rotation with respect to the second mass. First one is going to be 0. Okay, second one is going to be r2. All right, so just imagine that this length is L, and that's it. Now we came up with a mathematical expression for the moment of inertia of this system that we're looking at. Okay, so straightforward. If I were to change the point of rotation, okay, so I'm rotating this one with respect to first mass, and this is the moment of inertia that we get for that particular system. So what would happen if I were to put the point of rotation right in the middle somewhere? All right, so this is case number 2. What I'm going to do is now I'm going to rotate both of them with respect to a common center. All right, so this is going to be my point of rotation. So everything is going to be rotated with respect to that point. So what happens to the total moments of inertia? Okay, so moment of inertia, the first one is going to be m1 times r1 squared. The second one is going to be m2 times r2 squared. Okay, imagine that these distances are the same. This is the total length. So r1 and r2 will be the same, so both of them will be half the length. Also, imagine that m1 and m2, they have the same mass. All right, so we end up getting, you add those two up, it's going to be 2mr. R is going to be L divided by 2. All right, so this is going to be L squared. It's going to be divided by 4. And then we end up getting a formula that looks like that. Okay, guys, depending upon where the point of rotation is, notice that in this case, moment of inertia is going to be much larger if you're spinning one mass with respect to the other one. All right, so this is going to have a much larger tendency to keep on spinning, or it's going to offer much more resistance to change of motion. Here, if both of them are moving with respect to the common center, moment of inertia is reduced, so which means that the tendency for it to retain sensation motion is reduced by half. All right, so the moment of inertia is going to depend on the point of rotation. Okay, so speaking of the point of rotation, okay, remember the guy who ended up falling after from the tightrope? This is what Nick Walenda. This guy is the grandson of the guy who fell and died in 1977. This guy is real famous. In fact, this is the guy who ended up doing the walk here in Chicago a number of years ago, blindfolded between two buildings that we're going to look at. Okay, so notice that these are tightrope walkers, have these long poles, and what does the pole do for you? Here's what the pole does, guys. Take a look at two poles. If you're holding the pole right in the middle, it's going to offer it's going to give you a lot of rotational inertia. Rotational inertia is the moment of inertia. Okay, it's the rotational mass. Okay, so what happens is it's got a certain amount of length. It's also massive. The bigger the mass is, obviously, the bigger the inertia is. The longer the mass is, the larger the inertia is going to be. What it does is it offers, larger the moment of inertia is, the larger the resistance to change in motion is going to be. All right, so it's going to keep you steady. That's what it does. Okay, so they make it as long as possible, and then obviously there's going to be a lot of resistance to rotational acceleration. It's going to offer a lot of resistance to change in rotational motion. So the only thing it does is going to make you steady. So you can lean on it from this direction and that direction. And then it's going to make it very easy to walk. And that's what they do in essence. It gives you a tremendous amount of rotational inertia. All right, so this is his Nick Walenda's.
Let's do this, baby.
Chicago.
Thousands of people packed the streets below to see Nick Wallander complete the walks 50 stories up in the air. His father was in radio contact, occasionally offering some unhelpful advice.
Nick, if you get a chance, give it a bounce one time so I can watch the reaction.
It's moving, Dad. I'm not going to give it a bounce.
All right.
This first walk, on a 70-foot incline, was broadcast with a 10-second delay in case anything went wrong. It took him under 7 minutes to make it across.
There we go. Praise God. God be the glory. I think you probably saw me shaking like a leaf. That wire was shaking underneath me, and, I just wanted to make it to the other side. I wasn't going to think twice. I was getting the wire I'm going. So I need everybody to be nice and quiet for me, okay?
Shortly after, he did the whole thing again, blindfolded, and this time in just over a minute.
3 feet.
One more step. Grab it.
The crossing saw him set 2 world records.
Love you guys.
It's crazy. All right, so that's what it does. Okay, once again, the moment of inertia is going to depend on the point of rotation. All right, so if the point of rotation is in the middle, this is the amount of rotational inertia you end up getting. If it's with respect to the end, notice that this is going to give you a lot more rotational inertia with respect to that point. Okay. So speaking of rotational inertia or the moment of inertia, notice that different shapes will offer different amounts of rotational inertia. Okay, the particular shapes that we're going to be focusing on. All right, so you got the first one. It's important. Solid cylinder, this one is going to be important. All right, so you got the hoop, it's going to be mr squared. Solid cylinder is going to be half of it, 1/2 mr squared. The uniform sphere, it's going to be 2/5 mr squared. All right, and we will also get to use this one at least once. All right, so those are the ones that we'll focus on. All right, so just for the hell of it. This one. So we got 2 masses. Okay, both of them will have exactly the same amount of mass. But which one has a larger rotational inertia? Okay, so which means that this time you have to use the solid cylinder. Masses are going to be the same, but one with a larger radius is going to have a larger amount of inertia, rotational inertia. So this one is going to offer a much larger resistance to change motion, or it's going to offer a much larger tendency to retain that rotational motion. So larger the radius is for a given mass, the bigger the rotational inertia. Okay. Problem number 9. Let's do simple calculations so I know you guys can actually handle this. So calculate the moment of inertia of a bicycle wheel. So we know the radius diameter of the wheel. I'm just going to use this as a radius. And the rim and the tire have a combined mass. So we know the mass, we know the radius. It says diameter, but I think I'm going to use that as a radius. And then, okay, so whatever. Okay, so we're trying to figure out the moment of inertia. This is meant to be a simple exercise. So I decided that it's going to be the radius. Okay, centimeters to meters. Okay, so move the decimal to the left twice. That's all you have to do. Our mass is given in terms of kilograms. And the moment of inertia. Okay, so I want you guys to be able to just pick the right formulas from, so it's going to be a thin hoop that we're interested in. So we end up getting mr squared for that. That's it. Now I'm plugging the numbers in. Then it's going to give us the moment of inertia in terms of kilograms meters squared. All right. Just know how to pick the right geometries. All right, so this takes us to the next point, rotational kinetic energy. We got a rotational kinetic energy. Oh, it's going to be interesting. All right, rotational kinetic energy. Here's your linear kinetic energy. Translation. All right. Okay, I was going to say translation. Just hold that thought. Okay, so here's your linear kinetic energy. Express the linear speed of the tire or the center mass of the tire, in this case, or the point of rotation, in terms of the rotational speed. So rotational speed times the radius of the wheel is going to give you the tangential velocity of the tire, the point of contact. And so square this term. And notice that mr squared is going to be our rotational inertia, or moment of inertia. The back substitution. And now it gives us the rotational kinetic energy of the tire. So go from linear kinetic energy, this is also known as the tangential kinetic energy, translational kinetic energy. The translational kinetic energy refers to the center of mass is going to keep moving linearly, so that represents the kinetic energy of the center mass of the tire. And this represents the rotational kinetic energy of the tire. All right, so KE sub R represents the rotational kinetic energy. Sometimes instead of using R, we use theta. It means the same thing. It refers to the rotational motion. So I is once again our moment of inertia. Omega is angular velocity. All right, kinetic energy is going to be expressed in terms of joules. Okay, this is known as the tangential kinetic energy or translational kinetic energy. Okay, what else do I have? That's it. All right, let's take a look at a simple problem. Okay, so we got a centrifuge. It's a rotor. It's centrifuge. So it's got a moment of inertia. It's given to us. All right, so how much energy is required to stop it from 8,250 revolutions per minute? All right, so what is the amount of work needed to stop it? How much energy is required? This is the amount of work required for us to stop it in terms of joules. It means the same thing. So bring it to from rest. Oh, okay, so I'm reading it wrong. Okay, so we have to kind of accelerate it to 8,250 revolutions per minute from rest. Okay, cool. Initial speed is going to be 0 radians per second. Final speed is going to be in terms of revolutions per minute. It needs to be expressed in terms of radians per seconds. Okay, so how much energy is required is what is the amount of work that needs to be done, or how much kinetic energy needs to be given to it. That's the same thing. All right, so work is how fast. Okay, so the work represents the amount of energy transferred, so the amount of energy transferred is going to be transferred in the form of the rotational kinetic energy. Instead of using R, notice that I'm using theta, it means the same thing. So the rotational kinetic energy is going to change. It's going to go from an initial to a final value. Initial value is going to be 0, so it reaches the final value within that time period. All right, so plug the numbers in, and we are done. It's going to give you a number in terms of joules. I prefer to express it in terms of calories, so it's going to be 3 calories of work. That needs to get done. Okay, so the total kinetic energy is going to be a combination of the rotational kinetic energy and the translational kinetic energy. All right, so when you add them together, it's going to get this is the translational kinetic energy. So this is the kinetic energy of the center of mass, and this is the rotational kinetic energy. So you can just sum them up. When you sum them up, it's going to give you the total kinetic energy of the system. All right, so it's like a tire. When the tire is rotating, it's going to have 2 types of kinetic energies. One is going to be the rotational kinetic energy. The other one is the kinetic energy of the center of mass. It's going to be moving linearly. Okay, let's take a look at that and then go take a break because I'm going to do a few mind thrusters. So we got a bowling ball. It's got a mass, and then it's got a radius. So it's rolling down a lane at this speed. So we know the speed. It's going to be expressed in terms of meters per second. So what's this total kinetic energy? All right, guys, the bowling ball is a good example of rotational as well as the translational kinetic energy. It's going to center of mass is going to be moving at the speed. And also it's got rotational motion because of its rotational motion. It's also is going to have a rotational kinetic energy. So it's going to have a translational kinetic energy as well as a rotational kinetic energy. So translational kinetic energy is related to the speed of the center of mass, and the rotational kinetic energy is related to rotational motion. Okay, so rotational motion requires that you have a rotational mass. So that's going to be I. So because we're dealing with a bowling ball, we need to figure out what we need to use for that. So obviously we have to use the form sphere. So it's going to give us 2/5 mr squared. So that's what we need to use. I do a back substitution. So adjust the terms here. If we have the like terms. Okay, so exactly. It must be late at night. Okay, guys, this is v squared. Don't forget that. These are v squared. I'll make a correction shortly. All right, so the angular velocity times the radial distance is going to give you the linear velocity at that point. So the angular velocity times r is going to give you the linear velocity. So that's your linear velocity term. Okay, this is not r squared. This is v squared. So I'm going to make a correction, make a correction, make a correction. All right, so you got mv squared, you got mv squared. All right, so factor out the common terms. All right, and you need to have a common denominator here, so it's going to be 12. Okay, what do you have? It's going to be 5. This is going to be 270 divided by 10. Okay, so that worked out. Okay, so this is the final expression for the kinetic energy. So let's just take the numbers in. Kinetic expression in terms of joules. I think that's as far as I'm going to go.